Let's see if it can start streaming. Hey, it's pretending to stream. That's a good sign. Welcome everyone back to the third Arduino Workshop. Can you guys put your hand up if you haven't been here for the last couple of workshops, please? Put it straight up so I can see all the people. So keep your hands up, sorry. Keep it straight in there. So the group back and all that. You at the front, not feeling with you, sorry. I'll try and help you catch up with speed. I'll try and help you guys catch up as well. And serious Navy man down the front. Awesome and nice. For those who haven't been to these workshops, we try and teach you quickly from scratch how to get Arduino working, how to program it, how to get some parts working, and how you can't get some processor like that together. Many university courses might teach you everything currently from the theory point of view. We try to get your maths done. This has been our last workshop this semester. If you missed out on it, or you know people who want to come to them, we do rerun them every semester from scratch. So generally starting around week 3, week 4 of each semester we do them. And the other thing you got also from the design house this time. We normally run a crash workshop at design as well. If you guys want to, if anyone you want to really crash workshop from scratch, basically these 3 workshops trying to be condensed into one and be crazy. Week 9, I'm going to be running another one of the Art Design this semester. Anyway, I'll stop yabbering on. Today we're going to be looking at, the past few weeks we've been looking at some very basic interfacing. How to talk to parts using the wires, how to send signals to them, and also how to do parts to send signals back to Arduino, things like buttons, light sensors, stuff like that. I'm going to do activities where you do the code yourself to try and gather data from those sensors, and then you make decisions and do things like turn the lights on or do things like that. A lot of the time, when you want to do something, instead you buy what's called a module that does all the work for you. Good example is one of these guys. Your kids can have at least one in there, they're called a servo. They're a little motorized guy. There's 3 wires, one for power, one for ground, and one for signal, and you tell an angle you want to move to. So it's got a little rotary white thing out the top that you can attach this to, like fingers and spikes and harpoons and bayonets. A lot of people use the projects to make hands, weapons of war, death. I've talked to people who know, I forgot what they're called walkers. You've got people in a room and it's a game trying to have to follow the clues to get themselves out. Escape room. Yes, are you working on escape room? No, it's awesome bananas. So it's really fun. Today we're going to be going through not how to use them directly yourself, but how to use someone else's code to use them. A lot of the projects on the time you don't want to write all the code from scratch because it might take dozens or even hundreds of lines of code to get some devices working. So it's not going to cheat to use someone else's stuff. Welcome on up. There's someone else's step. Welcome. Another module we're going to go through today, I'll show you a bit. I'll stop the other one, so I'll move on. A distance sensor, and then at the end I'm going to be talking about a few other modules we don't have in our kits, we can get working, and a few other things. So anyway, starting up with a servo. Now I'm going to be running this bit of a hybrid workshop. Some of the side full, some of them I don't. With something like a servo, we can use a library code that sends it signals telling it where to move to. The actual way it works, which I'll get John to explain in just a second, is over one of these wires here, you send, do you guys remember pulse width modulation from last week? Look at that, because you remember it 100%. Oh, awesome. Basic premise is, we're sending a signal over a wire, is the voltage, it's either 0 volts or 5 volts, or we can turn that on or off. We wire that up to the servo here, the Arduino controls that wire, makes it 0 volts, makes it 5 volts, and by doing the practice of 0505, we can send the information. Last time we were using LEDs to dim the brightness of an LED by having a certain amount of time it's on, like on 90% of the time, off 10% of the time, about 90% brightness, varying that. I'll get John to explain how it works exactly with these guys. Well, we're not going to be doing that directly. We've got some other codes that do it for us. So, one of the things always to do when you're starting an Arduino project is Google stuff. Google stuff like hell. Arduino and the part name. In this case, servo. Luckily, servos are a very, very popular part, so the Arduino websites themselves have documentation. However, don't be afraid looking at other people's guides. Just make sure always to try multiple, because for every good guide, there's a crappy guide that makes no sense and they make mistakes in like typos and everything in their code everywhere. Now, in the Arduino environment, there's actually a thing called the servo library, which I'll quickly show you how to use and what it does. If I open my copy of the Arduino software open, can you read that? No, that is way too small. Give me just a second. The way we've been doing our code so far is that for every single pin we use, we've been going pin mode, giving it a number, and telling what we use it for, output or input, and then later we've been digital writing to it. Because we're going to get some other code to do our work first of all we need to tell Arduino we're going to be using someone else's code. In this case, we're going to be using a piece of code called servo.h. This syntax here has to include servo.h, tells the C or Arduino environment there's some other guy's code in a file called servo.h, let's use it. And then the way we're going to set this server up, where we're going to wire it to Arduinos is, as I said, one wire goes to ground, one wire goes to power, another wire we send signals over to one of our digital pins. We have to create a servo object. I'm going to call mine Bob. Servo Bob. I like Bob. He is a very faithful servo. He always turns in his sleep. We can then write bob.attach to set him up on the right pin. I probably have that. There we go. And the pin you attach him to, let's say I attach him to pin 3. And later, when you want him to move somewhere, you can do bob.right and give him an angle in degrees from 0 to 180. So I might tell him to move to 90 degrees. I'm just going to do an example program here. I'm going to get you guys to play with it and work out how to wire this. Delay for a second and then tell him to move to another angle. Let's say 160. Delay 1000. So I'm going to throw you guys at this in a second. I'm going to get Joel to come up in 3 seconds to explain how the signals work. However, the first thing I want to say is that the color coding on these servos is very confusing. Typically in the electronics world, black means ground, red or yellow means power. We have brown, red and yellow wires. The people who make these servos hate you. They hate you all with a passion. The brown wire is the brown wire, and because I'm a very bad person, I do not remember if it's the yellow wire or the red wire that you apply power to an analog signal. So I encourage you to try both, see which one works. See which one gets your servo moving and coming to life. Joel, you want to come up and quickly explain how the signals work?
Okay, so I just want to say servo is probably the most awesome thing used with an Arduino because they actually physically move. So there's so much that you can do with them. It's mind-boggling. They use servo signals for controlling drones, for controlling remote controlled helicopters, planes.
Yeah, the planes and stuff, they've got little surfaces on the wings, like flaps that you move up and down stuff. I've also seen robots that use nothing but servos to move the legs so they can actually walk about. And the exact same size that you guys have here, these are your ones. You can get my bigger ones.
Yeah, so they're so simple, but there's just so much you can do with them. And there's so many various types of servos. So probably those little blue ones that you have, those really cheap ones are really good to learn with. But there's some very, very high-end servos that they use in drones, in the military, and all that kind of thing. And they're really reliable, they're really fast, they're really, really powerful. And there's just so much that you can do with them.
So, Joel, in your military experience, have you ever crushed someone with a servo?
Crushed someone?
Yes.
Probably myself. They use servos everywhere, so they use them in factories and aerospace. Anyway, so with that said, I'll just go over what a servo actually does and how it works. It's basically, as you can see by holding it, it's just a box. But there's three wires. One is negative, one's positive, and one's the signal.
Don't trust the remote.
Yeah, well, they actually wire them onto the connector so that the positive is always in the middle. So if you connect it the wrong way, it's not going to just burn it out.
Yes, Joel actually knows.
So anyway, I believe that last week you were using PWM to turn on and off an LED light and to dim it. Servos don't actually use the PWM signal to power themselves. They use it as a reference to find out what position they should move to. So with that sort of theory behind it, you can actually apply large amounts of power onto the positive and negative terminals with just a very weak little signal from the Arduino. So you could use an Arduino to control as big a servo as you like, whether or not you really want to do that. So this signal here, there's something to clean it off.
No, we don't.
Okay, I'll just poison my hand.
You need a servo with a little rod attached to it. Up there's an instrument.
Yeah. Okay, so yeah, you guys covered PWM last week, and it just alternates between high and low. But servo signal is actually different to that in the sense that it's the width of the pulse tells it what position to go to. But the width going from low to high and back to low again, and then repeating. The only thing that the servo cares about is how high it's on for. The actual low time, it ignores. So you can have that low for a whole second, and it won't make any difference to how the servo runs. And this width is 1,000 milliseconds, 1,000 microseconds, all the way up to 2,000 microseconds. But this time, this low time here could be as long or as short as you like to a point. So between 1,000 microseconds and 2,000 microseconds, that's really, like visually speaking, if you were to look at the signal, it's really not that much of a variation when you look at the entire signal. So anyway, I'll show that to you guys later when you actually get your servos running.
Yeah. If you guys want to do this activity now, I'll open the code back up. Joel, I think, had the right wiring there, where it was positive in the center. So this is your servo, 3 wires coming out. The brown one is negative to ground. The red one is positive to 5 volts. And the other one on the other side is for signal. Have a that now, see if you can get snaps, see if you can get your servos moving. Modify the codes so they do different things. And we'll go around with your hand and then we'll move on to the next activity, which has some other cool parts.
Can we go back to the code again?
Oh yes, no, I said that was going to open up, wasn't it? There we go.
There's a curly graphic on there.
1 minute. There we go.
No, sorry. But the next activity is on the last one.
We've got 3 wires. Brown one needs to be connected to ground. I'll label it ground there. Red one needs to be 5 volts. Yellow one needs any additional things you want. Just ignore 0. Well, you did this with red. There was an idea in previous years we include lasers in the kits. We attach lasers to servos and everyone try to blind each other. Automatic. Unfortunately, someone said that wasn't a good idea. Oh, and your kits, there should be little plastic parts you can put on the end of your servo so you can actually spin stuff. Little plastic fittings you push on. Well, the connector has a servo with its magnet and hanger. Alright, so you guys have got to make sure they're working. Then I have to, sorry, push on the next section. The other boring bit, or the most boring bit. These are Program it to press the button on your keyboard after the stage. So every time they'll just skip every time. Stop programming Arduino. I'm sorry guys, I might move us all on here because I have to apologise to people who don't have servos. If I could grab everyone's eyeballs, people at the back, if you could all put your stuff down, just turn to me for a moment. In a few minutes from now, one of you guys can steal one of your things up here, and Joel, we can see what the waveform, the signal it's actually sending out, is on a what's called an oscilloscope that measures it out. But what I want to tell you about is another cool thing you can hook a servo up to, which is known as a potentiometer. The thing on the right of this picture here is what's called a clock or a potentiometer. It's a little very normal. Last week we had a light gate resistor and a resistor, and we're using those to sense light. A potentiometer is two resistors that vary. So by turning them on, if you remember from last week, we can get different voltages out of it. So you can actually write some code that reads what the clock's doing and then tells the servo to go to that angle between 0 and 180 degrees. So as you turn your clock, the servo moves to match it. So the whole bunch of clocks you can have manually operated robot, all sorts of other cool things. Now, the next part which we're going to do, which I'm going to hand out in just a moment, is called the ultrasonic distance sensor. This guy, if you have a comprehensive kit, it'll be in there. If you don't, I'll load it out, so don't worry. I'll have a picture up of one of these. Here we go. These guys, if you have a look at them, they've got what look like two little speakers on the front of them. And they are literally speakers. One of them's a speaker, one of them's a microphone. And the way that these guys work is that they send a little pulse of sound out one speaker, and sounds in air travels at an approximately known speed. The sound then bounces off something like a wall, a person, your victim, things like that, comes back toward the sensor and gets picked up again. If we know how long it took for a bit of sound to go out and come back, and we know the speed, we can actually work out its distance. So these things can be used to sense distances from a few centimeters to a few meters, relatively accurately. I had a guy trying to show off his amazing new laser distance meter one day, and it was absolutely garbage actually. He paid a lot of money for it, it wasn't working right. We got one of these out, and we really annoyed him. These things are absolutely brilliant. They cost a ridiculously small amount of money to get one shipped to your house. Always recommend buying multiple. Great also sells them. We find a variety of prices. If you find anything that looks like these but is slightly different, assume what's known as the law of Chinese packaging inertia applies, where if it looks the same, it is the same. These are a very popular hobbyist part. Now, with the servos, that servo.h got a whole bunch of code behind the scenes to do the work for us to control that servo. With these guys, that code isn't included with the Arduino software, so you have to download it from the web. We're literally going to look up on the web, and I'll go through it now and show you how to do it. There's a beautiful library called NewPing up on the web. And if you guys watch me just doing this, literally just going to search up NewPing Arduino. It will come to the Arduino Playground, which is a site where people provide lots of code. There's all sorts of other sites and sources as well. And somewhere hidden in this page, where you're least likely going to find it, is a download link. They are horrific. Oh, no, they actually labeled it on this one. I was dealing with a whole bunch of libraries on the weekend, and not one of them had an obvious download link. Some of them were just random numbers hidden in a corner in a sentence. And it has taken me to the Arduino store. It is a very reliable website today. Let's try that again. Here we go. It's giving me a couple options. Zip files. The libraries you download most of the time are going to be in zip file format. I'm just going to save that anywhere. That's going to be in my downloads folder. Now, this is the important step you all need to pay attention for. I need your eyes. I'm sorry, guys, this is the third week, and I'm losing you already, and some of you didn't come to the previous workshops. I'm sorry. In the Arduino software, you want to go to Sketch, Include Library, and Add Zip Library. The Arduino software can't find your library until you tell it where it is. In this case, it is in my downloads folder, which I should be able to get to up in here. Or not, because it is a particularly fun computer, and I'll never find my downloads folder again. It looks like I'm never going to find my downloads folder again. Where is this located? This is located in my downloads folder, which on this MCIC laptop is a bit of a pain to get to. So I'll cheat. No, that's not what I wanted to do. Oh dear, I am the best demonstrator in the world. Thank you everyone for watching. Downloads. Here we go. And I downloaded, it was called NewPing version 1.8. I hit open, and the Arduino software will say library added down the bottom. All good. So I can now use this library. The way we use this library, if I go back to the code, is again quite simple because it does most of the work for us. The way, I'll talk about just quickly how it works. I've written an imaginary function here, something I haven't introduced you guys to this semester, so please ignore the bit of code at the top of the bottom with the extra curly brackets. What we basically do is we create an integer, a number, called echo time, or whatever I call it. We're going to store the time it takes for our pulse to leave our sensor, come up again, and be received. So, what we do is we run a command. I've called my sensor thread. Last time I called the servo volt, I had a very bad memory scheme. Please don't command this game. And I tell it dot ping. Ping is slang term for sending a little pulse of noise out. It sends a ping of noise. These sensor modules output around a 40 kilohertz noise. So for the most part, we can't hear it. You're not going to hear a bit of a click. It also makes while it's doing it. It will really, however, annoy cats, dogs, and rats. So please don't go irritating animals. Please irritate humans instead. And then what we can do is calculate a distance. And we simply divide the echo time by how long it takes for the sound to travel a centimetre. There's a bit complicated way I've written that here. Last week I mentioned how we need to remember numbers. And whenever we tell it to remember a number, a bit like algebra, we actually have to tell it what type of number it is when we first use it. So the top echo time is int, or an integer, or a whole number. The second line, distance, it's a floating point number. Basically speaking, it's a decimal number. Floating point computers is a way of representing decimal numbers. We say distance is the echo time slash mean divided by US round trip centimeters is actually a number, believe it or not, it's another variable, one we haven't made, but has been made in the newping.h header file. And I'll do a code example on how to use it. And so once I've run those top two lines, distance now holds the distance to the object in centimeters as a number. So those are 2 lines of code, and your sensor will send the thing out, wait for it to come back, and give you a number in centimeters with decimal points after it. So, I'll do a quick example up now. Other thing always refer to is under the documentation for ping libraries, they'll also, or any sort of Arduino library, they'll give you an example piece of code normally. Alternatively, what you can do, if you're particularly lazy like me, is if you go File and into Examples, all the way down the bottom, there'll be the examples for the libraries you've installed, include NewPing. And there's just a simple one called NewPing Example. And it's very, very, very simple. It has hash include newping.h. It defines, I haven't shown you hash defines before. They're basically a bit like variables. A word equals a number. We're telling it a pin, a couple of pins we've got it wired to. We have to create the object. I'll rewrite this to be a bit simpler. And the way they've got it set up is they're using serial communications to get it back. So what I'm going to do is I'm going to quickly rewrite this and show you how it works as well. So this device physically is got 4 wires total attached to it. 2 of them for power, just like we did the servo. However, it has 2 signal wires. One of them is what you use to tell it to send a pulse of sound out, and the other one is what you listen to in Arduino to see when the pulse comes back in. So one of our wires is an output from the Arduino, the other is an input. The output wire, we literally have 0 volts, we tell it 5 volts for a split instant, turn it back down again, and then off forever. While this is up, the little module will be sending a ping sound out. Another ping we're listening to called echo ping, we'll simply wait until we get pulses of sound coming back through the module. Now, because the room echoes, as in sound has multiple parts it can take and get back to at different times, you'll actually get multiple pings coming back. However, the software is smart enough that this takes the first ping, which should be the closest object. Sometimes you never get a reply back, in which case the NewPing library will actually just give up after a while and say 0 centimeters or 3 meters or so on and so forth. I might actually start handing out these cards. So if you guys want to come and collect the cards from here in just a moment, I'll pass it around. I'm going to write some example code up. So just wait 1 second. What I'm literally going to do, sorry, I've got conflicting instructions. Newping.h. And then I'm going to create an object called, if I can remember the syntax, it was that one. Copy and paste that. So, the first pin, I'm just going to leave the words trigger pin there. Please put the number in that you wire to the pin labeled trig on the module. I'll show you these in a second. In fact, I'll show you the picture back again. Some of you guys will have these in your kits, some of you won't. You have to borrow them. You notice that there is 4 pins on this. VCC and ground, which is power, then trig and echo, which are the 2 data ones. And if I go back, trigger pin, echo ping, and you give it a max distance that you want to go be looking for. Now, the max distance is in centimeters. So, generally speaking, putting a number in there like 200 or 300 centimeters is generally good enough. Then, for our void setup, I don't believe we actually have to do anything. And what I want you guys to do, I'll do a void loop, float, and I'll copy and paste the code we had from back there. Which is this guy. Now, who here remembers how to do serial communications from last week? Anyone? I'm going to ask you guys to see if you can work out from the stuff we did last week how to do serial communications. Have a go at trying to remember how to do it. We basically want to set up the serial communications of our computer so we can send and receive text to our computer. And then every time we take one of these measurements, we want to send that measurement to our computer so we can see it on our screen. So we're going to have a little module hooked up to our Arduino, and every time it takes a distance measurement, we will see them come out on the screen. So this is actually incomplete code here. I'm going to leave you guys have a go at that for now. Look up the new Ping library, download it, try have a go at doing this, and if you've forgotten what to do, feel free to ask, we can help you out. Click one of the modules you're trying to do out, and please return it when you're done. And have a go at this, have some fun. And the next activity we're trying to find some things.
If anyone wants to see their servo running on an oscilloscope, see what the signal looks like, feel free to come up and let's connect up and I'll show you.
Make sure you look up new ping, not ping. Ping and new ping are different libraries, just to be confusing. Justin says two Arduino companies and three of them.
Is there a wiring diagram for this?
It's written on there. So what you do, VCC and ground, you hook up the 5 volts and ground respectively, and then the two other pins, trig and echo, you hook up to any digital pin that you want. Because one of them is we're going to be controlling digital logic, and the other we're going to be listening to, whether it's 5 volts or 0 volts, to see when we get that pulse back of 5 volts. Yeah. Yeah, look, quite a few actually weren't here in our first workshop, so you're going to be very confused at this point because I'm talking about some electronic concepts you've probably never seen before. So what I'll do is I'll try and find them and show you. So, come on, web browser of doom, load before me. Alrighty. Okay. Now, people who are new to this workshop, I'm going to grab your guys' attention for a bit. People who have been in this workshop previously, please keep working. I will start in just a few minutes. Right. Everyone new, can I get you to put your stuff down and give your eyes to me? If you haven't been to these workshops for the last couple of weeks, if I can steal all of your eyes, especially the people at the back, shady characters at the back. No, welcome you. I'm glad you've come along. I'm just sorry. It's not the most fun experience for you if you haven't been here previously. Arduinos, very quickly, are basic desktop boards, are basically small computers. The only things that they're capable of are, on the pins on them, they can listen to things called inputs that give them signals. They can tell things called outputs what to do. They can waste time, they can make decisions, and they can repeat themselves, and that's all they can actually do. Listen to stuff, say stuff, waste time, make a decision, nothing else. And so the way we normally wire up a project is, for example, in a robot car, an output from the Arduino will be the motors. You want to control the motors to make it drive. You want to tell them what speed to go. So the Arduino tells them, go on an Arduino. And you have inputs like a light sensor or to detect a wall or distance sensor to see if you crash into something to change how you're going to be driving. Two very quick important concepts: electricity. All the stuff that we talk about in Arduinos has to do with voltages, how they control their wires. If I go back to a picture of an Arduino, along the entire top side are what are called digital pins. Those little black holes you can put wires into. Pins 0 to 13. Those pins, the Arduino can either drag them to 5 volts, and any wire you have connected into them also gets dragged to 5 volts, or drag them to 0 volts, also known as ground. So if I hook up a light to those, I can turn that light on and off using that. Alternatively, if you hook up something like a button to them, you can get the button to pull the pin to 5 volts, 0 volts, hook up one of those, and the Arduino sees or listens to see if it's 0 volts or 5 volts. So you can have things both go in and out. We're hooking this up to the distance sensor so that we can send it 5 volts for a short time and then back to 0, and listen for it to do the same thing back to us. So unfortunately, very, very quick crash course. I'll put the code back up. Feel free to ask lots of questions. There's no such thing as a silly question, only a silly lecturer. You never. Oh, you called your my son up. Okay. You went for a serious attack or a non-serious one? Yeah, I got violent. Or whatever it is. Combination. Try scrolling first here. Oh, we haven't installed a new one. You need to install a new library. Yeah. Use numbers you can look at the internet, you can download the zip and as I show you guys how to do it if you want. So once you download the software, you go you go into sketch. It's not sketch now. Two libraries. It's that first one you do that. This is what I'll come back to my I just want to share screen, not some custom.
They couldn't see, so I had to zoom out a bit.
No, I can't use this one because How you guys going? Is anyone got anything working yet? Awesome, guys. It's a typical activity. And by the way, guys, I'm really proud of you. You're one of the first workshops that's come close to damaging the part. I've been really disappointed in previous workshops that there hasn't been any explosion. Actually, there might have once been a little bit of smoke, but that was it. I didn't even think that. Part of electronics all the time and learning is when stuff goes wrong, sometimes we collapse melt with horrible things. That's part of the experience. Embrace it, you learn a lot from it when stuff goes wrong. Although, trying to burn 200 miles an hour intentionally, please. I will need to explain to you the theory of smoke. So I need to grab, this is a very important topic that helps with everyone. Guys in the back, playgrounds again. This is a very serious topic here. Have any of you ever blown anything electronic up before apart from this, like release smoke? One, two people. So, the smoke comes out, it stops working. This has given rise to understanding electronics known as smoke theory, where if you put the smoke back in, it works again. At the end of the day, what keeps an electronic device working is the magic smoke. For various old cars where the electronics used to catch fire all the time, you used to actually be able to buy brand jars of replacement magic smoke. Unfortunately, no one ever got them working again. Anyway, that's all I wanted to say. Get back to work. Now, for those of you who have got a really sorry guys, one more time. For those of you who have got a wonky, the next activity you can go on to is use the measurement made by Ultron Distance module to tell your servo to move to a different position. Use below. Now we have servos we can load into you guys if you don't have a servo now. So if you want to grab one for fun, please feel free to do that. Otherwise, keep working what you do, try to get it working, put it in hand and we'll help you out. It's not like that. Guys, inside these guys, what they have is there are loads of these, and there's a little drawer that's controls that load. It's normally not going to come control load directly, but it's just going to current load. So it always has the same. This board only lets us servo the single circuit calibration things. You can get more advanced servos and do full reconciliation things from that. These ones zero areas. If you do that, it'll divide by 180 or also back to 0 or 180 or something like that. So it goes to the thing and it'll either way to misbehave if you done that side of it. Oh, you've already got it working. Cool. Thank you. Oh, okay. You don't need to. You haven't programmed.
I hear a robot army moving in the corner. Should I be afraid? One second.
Now, when you have if you've got it working, just the distance sensor working, you're seeing numbers. Put your hands in that. Where I saw you guys. Now, put your hands up. Put your hands up if you're still working on getting the distance sensor working. Proving the same thing up. Now, put your hand up if you've got your distance sensor, the number is recording controlling your servo. One guy, two guys, maybe. One guy. Awesome. Now, I'm going to get you guys back to that in a moment. I want to go again through the slightly new topic, motor control. So that we don't have the class for kids, but I can quickly tell you how it works. So if you make your own projects, you don't need to do that. Control motors is one of the more important and fun things to do with an Arduino because it's basically making robots. And in my opinion, is basically the whole point of it. Once that's done, we're going to have a look at fuzzing. I have to check your kids have the right parts. However, let's have a look at motor control. Alright, now in previous years we've actually had motor controllers and motors in the kits. Some of you guys have had this together comprehensively. Now, I want to grab your concentration while I'm talking. I don't talk for long, I hope. So guys at the back, if I could get you to all turn around and face me please so I can grab everyone's eyes. I love people's eyes. And people at the back rear. People at the back rear. Thank you. Just for a few minutes, I'm going to talk for a bit, then feel free to get back to this project and get back right where you want. I want to talk about a few final things. This is most of the final project for today. Unless you've got other projects and we don't all have the parts for, we can have a go working on. Otherwise, we're going to go clean this one. So let's talk about motors. As you may have heard me mention previously, you can't control a motor directly with an Arduino. Motors just suck too much electricity. The Arduino can't give it out. You need something in between. Now, most of your small projects are going to use one motor called a brush motor. You can identify by the fact that it has two wires. Any motor with two wires is very simple to use. You can use it in both directions. It's called a brush motor. They're cheap. We sell a few different types. You can pull them out of old things. If one of your parents is an Android and they fall apart on it, it's still parts out of them. All different shapes and sizes have been made for hundreds of years. They're great. But you need something between a motor driver. Motor driver basically, small signal from an Arduino turns on a lot of electricity to your motor. And in the case of these motor drivers, they can control brush motors in both directions. So you can make it forward or back, and you can also vary the speed. Usually, if you remember last week, we dimmed an LED by using PWM, turn it on and off very fast. We did the exact same with the motors to change their speed. Now, Craig sells a couple of different modules to do motor control. You also find a whole bunch online that looks similar or slightly into this. The basic gist of them is very, very simple. This big one here, I use as an example, so it's one I do recommend people to start out. This is the extra chip that does all the work for you. All of this here is just to make it easy to connect to and use. You've got two connectors there and there to hook up to two different motors. You can control two separate motors on this independently. The front here, you hook up power. You generally need a voltage. These ones it says on the bottom 12 volts, it recommends. You can run them low, you can run them high with a certain margin. And over here are 4 pins that we hook up to our Arduino. And using these 4 pins, we tell the motor what to do. Motors what to do. On this driver, these left 2 pins are for the left motor, these right 2 pins are for the right motor. Literally, one of these pins is for forward, one is for backward. If you have both at 0 volts, the motor does nothing. The forward one at 5 volts, it goes forward. The backward one at 5 volts, it goes backward. And both of them at 5 volts again does nothing. Simple control. There's actually a couple of wires hiding under these little caps or clips here. You can control it a bit differently. Some guys will show you how to do that. This motor driver is very similar. However, two motors at that side, 2 of these pins are for power, the remaining 4 again to control the motors. This one's a bit different. Instead of forward and back pins, you have one pin to turn the motor on and off, and another pin for the direction. So if you turn the motor on, it will go forwards. If you then change the direction pin to also be on, it will go backwards. Turn the motor off, equal the direction pin up, and just turn the motor off. So it's slightly different control scheme, does the exact same thing, and again, to vary the speed, one of those pins you pulse the modulator on and off to get it to different speeds. Feel free to have a go at that. If you do have parts in your kit today, I'll be able to help you out. The general way you wire up is your Arduino sends signals to your motor driver, which controls your motor, and each of those things needs power. If you want to run your motor driver with a computer, you can do it over the 5 volts. It will be a bit sketchy, and if your computer is particularly unhappy because it's drawing so much power, it will turn Arduino off and just reset all the time again on. Ideally, use batteries or another power supply to do it. Motor drivers are simple things. Internally, they're a bit more complicated. Always get them as a module. I don't recommend trying to build them unless you want to really hardcore. I've designed and made my own motor drivers before from scratch. It was a bit of fun. I then went overseas, and while I was overseas, someone blew it up. And by the time I got back, people had harvested parts off it, so I was a bit sad. But it was a lot of fun to do, but they're a bit complicated. And again, I always recommend people buy modules. Other thing you can do is that motors have big coils in them. How do you ever pull apart a speaker? What did you find inside the speaker? Magnets and coils. These are much more than magnets and coils. If you actually turn on and off these motors at the same frequency as a note, like I don't know if any of you musicians here, the reference point all the time is middle C, C4 or something is about 440 hertz, so around 440 times a second approximately. The motor will actually play alone. Because it's a coil, it's going to motor off at that speed, vibrating the motor at that speed. There's beautiful videos in the web. Who here's seen a 3D printer? Who hasn't seen a 3D printer? Oh, you guys. 3D printers have motors that move around in front of it. And there's great videos in the web of them playing with things like Star Wars theme. And then people get things like floppy drives, which have motors in them, and they hold racks in them playing music, and each of them playing a different amount of music. You do all sorts of cool fun stuff. Now, everyone here now, can you look at your kits? Can you see if there's a little black round cylindrical object in there? About a centimetre wide. The comprehensive kits, I think will have it. I want to know if your smaller kits do. Probably not. Do little microphones or buzzers? Even the comprehensive kits? I sort of wrote down some of that. Yes. They look like these little things. There's a few different variants. Some of them are basically a coil and a little diaphragm, a little speaker. Others have a cool thing called a piezo crystal, which, as far as minerals go, is the best at doing dancing. You put a little electricity on it and it literally changes size. There's actually, I'll give you a story now. I was talking about brain systems before. So let's say you're a blind person that needs instinct. It's a bit hard because you need a braille system that changes depending on what you're looking at. So these are electronically controlled. They had one where they had these crystals about yay long, each in quartz, and when you apply electricity to them, they got a bit longer. Or they vibrate. One of them, I can't remember. One vibration. So using that, they'll make a braille system for little kids. All sorts of cool stuff. But what I'm saying is that for the most part today, this is the end of this last workshop. I've tried to do as much more for you guys so far. I'm teaching how to use the Arduino, some basic code, how to do digital communications and analog, which gets to use a whole variety of simple sensors. And today, how to do a little bit of using libraries, so you can use other people's code. There's a lot more in the world, there's an infinite amount you can learn. I'm hoping, above all else, I give you guys a bit of confidence and maybe find stuff out and give things to go yourself and buy them. And not worry if stuff blows up because it's all really cheap. Like some of the LEDs are about a cent each if you want to buy them. If you guys have any other questions, feel free to ask me or any other helpers here today. If you want to keep hanging out with projects, the pigs will be here in a little while, another 10 minutes. Otherwise, it's been great seeing all you guys. I hope you have some fun, and I hope you use your ability skills to make some fun projects. So you're controlling the pin in the other time, analog so you have to be in your because you got all six things that you saw. Oh, okay. Did I take it back? No, that wasn't me. I might try the van and see if it still works. Oh, that's nice. Alright, pizza guys! Pizza outside! Was it you must probably be more than one reason that you tell them so fast. Take this with you, actually fast slow. It doesn't receive the feedback, it's play while we're picking up and hope it does receive the feedback. And that's why we get the max distance. The max distance is equal to how long it takes to bounce back from that distance if it can't arrive in that time to do something for return as well. Zero divided by 4? Yeah, zero divided by 4. It doesn't receive anything. It will be because if you got wires in front of your module at the moment, it might be bouncing those kind of things. So it might be worth using wires there. I don't know if you get that from my current screen. Oh, I should probably tell this to stop.